Okay, so today we're going to talk about the homework of chapter 4. Okay, so for the first question, we want to look at the problem 4.1. So for problem A, we want to calculate the multiple momentum QLM of the charge distribution of figure A. Okay, figure A. So in here, we can find that the charge density can be written as this form, where when r cosine theta is equals to 0, which means in the xy plane, and if r phi equals to 0, pi equals to pi over 2, pi and 3 pi over 2, we have the charge as here. So the charge density can be written as this form. Then we just substitute the charge density into the multiple momentums equation, which is integration of this term. So just for charge density into this integration, then calculate it. Okay, then by numerical calculation, we can get the final answers. Then you will find that if the m equals r, then this term will just this term. But when the n is even, this term will become 0. Okay, so in here we want to show the first two sets of non-vanishing. So for the first set is when L equals to 1 and M equals to plus and minus 1. So the result is this. And the second set is the L equals to 3 and M equals to plus and minus 1. Okay, so the result is as this form. Okay. And then we check the problem B. Problem B, we want to calculate the multiple momentums of the figure B. Okay, so first we just write down the charge density. Okay, so by similar way, we can easily get the charge density as this form. And then we substitute the charge density into the multiple momentums equation. Then by numerical calculation, we can get final answers this term. So the first two non-vanishing momentum is these two, when L equals 0 and L equals 2 and n equals 0, and L equals to 4 and n equals to 0. And then for the problem C, we want to calculate the potential of the figure A. Okay, the potential of the figure A. And sorry, the potential of the figure B. Okay, figure B. So we just, as we have calculated the multiple momentum, then we just substitute the multiple momentum we calculate into the relation here. And then we only left the lowest non-vanished term, which is this first term in the limitation of R is very bigger than A. Okay, so finally the potential will equals to this. So the potential will equals to this. And in the xy plane, which is when theta is equal to pi over 2, okay, this term will vanish. Then the potential will become this. And so we can easily to plot the figure as potential as function of R. Okay. And then in the problem D, we want to calculate the potential directly from the Coulomb's law. Okay, which is the exact potential can easily get the answers this term. So by comparison, the result calculated in the D and the C, okay, C is this in the limitation of R very bigger than A. So to compare these two, we just plot them in one figure and divide by 1 over R to the power of 3 to both, okay, and then we can find the result as this, and the straight line is the result C, and the slope line is the result D. So you can easily check that when R is bigger, these two results will get closer. Okay. Okay, then for the problem 4.2, we want to check the dipole can be written, it can be described by the effective charge density as this. So we know that the potential due to a dipole is equals to this term, and the potential due to a charge density is equals to this term. So to prove this, to prove the dipole can be described by the effective charge density, then we just comparison these two. Okay, so we know that we need to make sure the integration of charge density will equals to here pi dot this term. So to calculate this, we just expand this p, and we first calculate we first integrate the delta function to get the integral form, and second we just substitute this term by gradient 1 over s minus s prime and absolute value, which we have done several times. So you can check in the lecture note to chapter 1. We have this relationship, and be careful in this. We just we rotation with s prime instead of x. So you have to be careful of this. Okay. So to calculate this integration, we just use the integration by part. So you will find out that there will be two terms. And the first term, we can use the Stokes theory to change the volume integral to surface integral. And then we will find this term will vanish on the surface. So we only left the second term. Okay, we only left the second term. So we finally get the results this, and then we compare this to the charge density integration. Then you will find that the effective charge density have to equals to minus p dot this gradient. Okay, so we have to prove it. And then for the problem B, we want to calculate the same. We want to calculate the energy by the same approach. But in here, I don't use the same approach. So if you want to calculate it, you can check the A. And in the B, we just simply to put the effective charge density into the energy into the calculation of integration of energy. Okay, so we just put this in here, then we get this term, and then we just integration this by part also. Okay, integration this by part, and then the same we will have two terms. And the first term we use Stokes theory, and then find out that this will become 0 at surface. So we only left the second term, and the integration of delta function, and you can get that the result is equal to minus p dot external electric field, okay, which is the same as the result of our energy of dipole. Okay. And then for the problem 4.10, okay, here this is the boundary condition problem. Okay, so we want to find the electric field everywhere, okay, between the surface. And so we just use the Gaussian's law. With a Gaussian surface the Gaussian surface is chosen at R between A and B. Okay, so we know that this term will become d1 plus d2 times 2 pi r squared, where 2 pi r squared is the half of the surface area. Okay, half of the surface area, and is well equals to total charge Q. And we assume that total charge Q is equals to Q1 plus Q2, where Q1 is the charge distributed at inner surface where I equals to A in the region 1, okay, region 1. And the Q2 is the charge in the region 2. So in here, we have the first equation where is displacement 1 is equals to epsilon 0, where this epsilon 0 because it's vacuum. Okay, epsilon 0 times electric 1, which is equals to Q1 over 2 pi r squared. And the displacement 2 will equals to epsilon times electric field 2, which is equals to Q2 over 2 pi r squared. And then we apply the boundary condition at this boundary where z equals 0. And in here, we know that the parallel electric field have to be continuous. So the E1 and E2 must be the same in here. So we can get the result as this Q1 over epsilon 0 have to the same as Q2 over epsilon. So by this relationship and the result we have here, then we can easily get Q1 and Q2 will equals to this. And so the electric field will become this term in when R is when R between A and B. Okay, when R between A and B, and E will electric field will equals to 0 in all other position. And then for the problem B, we want to calculate the surface charge distribution. Okay, so we just apply the boundary condition where the divergent divergent D is equals to 0. Okay, divergent D is equals to 0, which means the normal electric field on the boundary must be continuous. No, must be the same as the surface charge density. Okay, and then we know that when R smaller than A, there is no field inside. So the surface charge distribution only equals to this term. And the electric field we have calculated in the problem A, so we just simply put it in, substitute it, and then we can get these two terms. Okay, just use the boundary condition of divergent D equals to surface charge density. Okay. And then for the problem C, we want to calculate the polarization charge density. Okay, on the R equals to A, on the surface of R equals to A. So we know that the displacement will equals to epsilon 0 times electric field plus polarization. So the polarization 1 in the region 1, okay, the polarization will equals to epsilon 0 minus epsilon 0 times the electric field, which is 0. So we know that in the region 1, the polarization is equal to 0. And for the region 2, the polarization will equal to epsilon 0 times the electric field, which is the same as this term. So we know that the polarization charge density will equal to this. Okay, you can easily check this relationship on your lecture notes. So the polarization charge density will equal to this on the surface of region 2 and will equal to 0 on the surface of region 1. Okay, so this is all of our solution we will discuss today. We discussed it today. Okay, so thank you for your listening. So if you have any question, you can ask me after the class. Thank you.